All right, so let's talk a little bit about chemical equations and how to balance them. A chemical equation is a symbolic representation of a chemical reaction. Reactants are on the left-hand side of the reaction. They're what you begin with, or what you put in the container to react in the first place. Products are on the right-hand side of the equation, and they're what's produced as a result of the reaction. We measure the relative amounts of each using stoichiometric coefficients. And that's what happens when we balance the reaction. We want to have the same number of each type of reaction, or each type of substance on both sides of the reaction. There's some symbols that are pretty commonly used. You'll see a plus sign read plus or added to, or sometimes and it's in between individual reactants and products. The arrows read yields or reacts to forms, and it always points from reactants to products. Sometimes it's important what state the reactants and products are in. So an S in parentheses means a solid, an L means a liquid, a G means a gas, AQ means it's an aqueous solution, which means it's dissolved in water. And sometimes it's a little old school, but you see that little triangle. Sometimes that's used to make heat, or it could just be the word heat, or there can be any number of things above the arrow on a reaction, a catalyst or a temperature or a particular solvent. And as you go on in chemistry, there'll be more things that you see that indicate reaction conditions. But chemical equations are an attempt to show what's on paper versus what's going on in the laboratory. So if we look at this reaction, we can see space-filling models of methane and oxygen on the reactant side, reacting to form carbon dioxide and water on the product side. And you can see we've balanced that reaction down below with 2 oxygens and 2 waters, but only 1 carbon dioxide and 1 methane. The reason is you can see how it balances. Where the grayish spheres are carbon, so you get 1 carbon, 1 carbon. You got 4 hydrogens, those white spheres, and then 1, 2, 3, 4 white spheres on the product side, so that balances. And then we got 2, 4 of the red spheres, and we got 1, 2, 3, 4 of the red spheres, indicating that particular reaction is balanced. And that's what we want to see for each reaction. Law of conservation of matter states that there's no detectable change in the quantity of matter in ordinary chemical reaction. Balanced equation should include the same number of each kind of atom on both sides of the reaction. So if we react iron oxide and with 3 carbon monoxides, add some heat, we'll produce 2 irons and 3 carbon dioxides. So the right-hand side is the reactant. That's going to yield, and it's going to form the products on the right. And so we can read that as individual molecules or formula units or ions or whatever you have. So 1 formula unit Fe2O3 reacts with 3 carbon monoxide molecules, goes to 2 atoms of iron and 3 molecules of carbon dioxide. Or more useful, we could use moles. So 1 mole of iron oxide reacts with 3 moles of carbon monoxide to produce 2 moles of iron and 3 moles of CO2. If we get the mass of those moles, 1 mole of iron oxide is 159.7. 3 moles of carbon monoxide has a mass of 84. And we'll find that's the same mass as you get on the product side, showing that if all the reactant is consumed, I'm going to produce the same mass of product. So that's all the masses are trying to show here, is that you get the same amount of stuff on the product side. So if you add those first 2 masses and compare it to the last 2 masses within a reasonable rounding error, you should have the same number. You say, well, what if I don't react up all of one of the reactants, which could happen? Then the amount of product formed plus any reactant you have left still has to equal the total mass you started with, or you're not obeying the law of conservation of mass. So what we're going to do is we're going to balance these 4 reactions and give you a little practice on reaction balancing. All right, let's look at balancing these reactions. So what you want to do if you want to balance a reaction, check and see if it's already balanced. And so we're going to use our knowledge of chemical formulas. So we got 3 carbons, 8 hydrogens, 2 oxygens on the reactant side, We got 1 carbon, 2 oxygens, plus 1 is 3, 2 hydrogens on the product side. So that doesn't match at all. One way of looking at that is that oxygen's by itself, and we balance it last to ensure everything stays balanced, because if I add a coefficient there, it changes the carbon and the hydrogen. So let's balance the carbon first. So there's a 3. So if I put a 3 there, it will balance the carbon, but it also changes my number of oxygens, which we'll come back to. 8, and so what do I need to get 8? I'm going to put a 4 there to balance that. 4 times 2 is 8. So now everything is balanced except for the oxygen. Now let's consider what coefficient I need to put there, because now I can put a coefficient there and not change anything else. So we got 3 times 2 is 6. 4 times 1 is 4. So 6 plus 4 is 10. That oxygen's in 2s. So if we put a 5 there, 5 times 2 is 10. And that reaction would be balanced. So let's apply the same strategy to this next reaction. Nitrogen's initially balanced, but likely won't stay that way. Hydrogen is not balanced, but oxygen appears to be. So let's focus on the hydrogen first. 3 versus 2. 1 doesn't go into another, so you find the next biggest number they go into, which is 6. So if I put a 2 there and a 3 there, it balances. But I've changed the nitrogen, now it's not balanced anymore. So if I got 2 of those, that means I'm going to have to put a 2 there to balance the nitrogen. And now I just need to see if I need to add a coefficient there to balance the oxygen. So 2 times 1 is 2 plus 3 is 5. But since oxygen comes in 2s, there's no way for me to really get 5 oxygens by putting a whole number coefficient. I always want the coefficient to be a whole number. If I add a fraction, say 5 halves, that balances it. And so if you've got an odd number of oxygens, it's always the number of oxygens you need divided by 2 is the proper coefficient to balance it, but I need a whole number. So what I'm going to ultimately do is multiply all the coefficients through by 2 to get a whole number. So that's going to become 4, 5, 4, 6. And you say, what if I hate fractions and I don't want to have to come up with that? When you realize that you can only get oxygen even over here, there's not anywhere else to take care of the odd one. Instead of doing the fraction, I could go ahead and double these coefficients and then come back for the whole number coefficient on the oxygen. Either way will work. All right, let's look at this next one, C7H16 plus O2, CO2, H2O. Nothing looks balanced particularly. So let's just go ahead. Now this one's a little bigger hydrocarbon than the first one. So we're going to have to work it just a little bit more. So we're going to start by putting a 7 there. Now 16, what 2 into 16 is 8. So I'm going to need an 8 there. So that gives me 16, 7. So now let's count up. 14 plus 8 is 22. 22 divided by 2 is 11. And so I'm going to stick an 11 there, and it balances it. The reason I work that is as hydrocarbons get big, even though the combustion reaction that we're looking at here is pretty simple, the coefficients start to get big as the hydrocarbon gets big, and there's nothing necessarily wrong with that. So don't let large coefficients throw you off. Let's look at this last one. We got aluminum sulfate plus barium chloride forms aluminum chloride barium sulfate. Now, what you need to realize in this one is the sulfate stays together. And sometimes when you get these ionic type reactions, if you see the ion has not been chemically changed reactant to product, I can balance that whole thing as a unit instead of balancing the sulfur and the oxygen separately, which in many cases can save you a lot of time and effort. So that's what we'll do. So we got 2 aluminums, so I'm going to need to put a 2 there. I got 3 sulfates, and so I'm going to need to put a 3 there to balance the sulfates. Now, hopefully, I can come back another coefficient here that's going to balance the barium and the chloride. If you notice, I got 3 bariums, 2 times 3 is 6 chlorides. So if I put a 3 there, that gives me my 3 bariums, and 3 times 2 is 6 chloride ions, and then that reaction is balanced. And so that should give you the basics of balancing a chemical reaction.